Thank you, everyone. Thanks to the organizers for inviting me, or for saying yes to my abstract, rather. Hello to all the internet people, all three of you who are watching me. I'm going to be talking today, shockingly, at a conference on space-time functionalism, about the function of space-time. And it's not quite, I didn't mean for it to be quite as facetious as it sounds, because I do think that there is quite a bit to be said about the function of space-time. It's something that Vincent alluded to when, during his talk, when he spoke about, when he sort of mentioned my name. So, you know, there you go, your shout out, Vincent. But the motivation behind this talk is, in a sense, slightly different from people like Dave Baker, whom Eleanor mentioned in her talk. I'm also looking at sort of the limitations, or at least the purported limitations of an Eleanor-style inertial frame functionalism. But I'm not looking for counterexamples in the hope that I'll be able to then argue against the functionalist position based on some kind of pre-theoretic, intuitive, however sophisticated it might be, intuitive notion of space-time. Instead, I'm interested in what makes space-time functionalism good and useful. So I'm sort of antecedently committed to it being good and useful. And I want to know why it's good and useful. And I worry that what I'm about to say might come off as trivial. I hope at worst that's what happens. I see the role of space-time, I see the function of space-time, as playing an important, I say role so much, as playing an important part in allowing us to theorize about the world in a way that saves us the trouble of having to do a lot of complicated physics, in a nutshell. And with this view of space-time in mind, I want to see what inertial frame functionalism tells us about slightly unusual, possibly space-time theories. And so, as Eleanor herself was saying earlier, we are, in a sense, engaged in a bit of conceptual housekeeping, if you don't want to say conceptual analysis. And she gave a very useful example of entropy and sort of why you might worry about whether black hole entropy really is entropy. And a really crude response to that is, well, if it is entropy, or if it behaves like entropy, then we can theorize about black holes using a lot of the physics that we have from thermodynamics that treats sort of other forms of entropy. And similarly, if we've got a notion of space-time sort of encoding certain useful features of our theory, then it seems like trying to figure out what plays a space-time role in a particular theory is sort of a good and useful thing to do. So to that end, here's the talk, here's the structure of the talk. I will extremely briefly, because we've already had 2 talks on space-time functionalism, talk about space-time functionalism. And then I'm going to present 2 slightly non-standard examples of dynamical theories and see what space-time functionalism has to say about the kinds of things that we can say about the world if those theories sort of happen to be true. So, in the back of my mind through all of this talk is really a conception of space-time, or a conception of the utility of space-time that was referred to by Vincent in his talk. I want to know in virtue of what the space-time conception, the space-time concept is useful, and that sort of splits into 2 parts. What is the space-time role, such that identifying this role makes identifying space-time useful? And secondly, how does it go? How does it play that role? And having identified this, can we then sort of use this to learn things about other theories? Can we suitably, apply a suitably generalized version to other theories, and then see if this concept is still useful? So, an oft-quoted Eleanor quote. This is from I think her most recent, a very recent paper on space-time functionalism, which, as you all know, I'm not going to repeat it. It's just up there, and we've been talking about it all this time. But I think there's a very interesting line that's sort of buried in there a few pages later, which actually speaks to what I take Eleanor's motivation behind spacetime functionalism to be. And I'll read out the quote. She says, "It's the fact that G mu nu, the metric tensor of general relativity, defines inertial structure that means that it represents geometry. This fact is not determined by the mathematical form of G mu nu." And I take that to be an expression or an acknowledgement of the kind of thing that Harvey Brown has been talking about sort of for many years. It's a thing that Jeremy Butterfield refers to as Brown's moral, which I think is a nice way of putting it, which is, you know, you can look at your theory, and you can find that you have certain mathematical objects in that theory. You can believe that those mathematical objects have some kind of representational relation with things out there in the world. But it's not merely in virtue of being a particular kind of mathematical object that that object will play all the roles that such an object can play, right? So for Eleanor, it's not the fact that G mu nu is a metric that makes it the metric that's surveyed by Matterfield. It's the fact that G mu nu defines inertial structure in the way that she went into, in the way that she spoke about in some detail in her talk, which I'm not going to repeat. And again, I make reference to the Dave Baker paper that Eleanor spoke about. Dave Baker's coming at this from a slightly different perspective. Dave is sort of from the East Coast of America and, well, studied on the East Coast of America and brings along with him a certain East Coast metaphysician flair. And one of the things that he's really interested in is fundamentality. This is what Eleanor mentioned. And so with that in mind, he says, look, inertial frame functionalism can't be the whole story, at least not if the goal is an analysis or explication of our space-time concept. And I think it's a deliberate wording. I assume it's a deliberate wording. And I want to focus on the word our. Because the question is, you know, whose space-time concept? And, well, in Baker's case, it's obviously Baker's space-time concept, which he takes to be a cluster concept, which is, multiple criteria of application. None of them individually is necessary, but a bunch of them together might be sufficient. And I think that's fine if you're sort of particularly liberal about the role that you think space-time plays in your theory. If you think space-time is the kind of thing that sort of ought to ground talk of causality or determinism or, modality, geometric possibility, whatever you want. And so, these are all the sorts of things that Dave mentions in his paper. And I want to be a bit more restrictive, because I think there is a very important role that space-time plays in our theories. And there are several very important roles that space-time plays in our theories, and I think it's important to have distinct names for all of those roles that space-time plays. So my version of this cluster concept idea is to think of three types of space-time, three roles that space-time might play, three things that looking for space-time structure might elucidate for us. The first is what I call theoretical space-time. And that's just the space, if you're thinking field theoretically, it's the space of independent variables of your field theory. It's sort of the structure that goes along with the space of independent variables of your theory. So it's it's a space whose geometric symmetries are the same as the dynamical symmetries of matter fields. The next kind of space-time, and this is the kind of space-time that people like Harvey in his book and sort of various passages of some of Eleanor's other papers seem to indicate they're interested in. It's what I call operational space-time. And that's a space whose structure is surveyed by stable measuring devices, things like rods and clocks. And when I say surveyed by, I mean, implicit in all of this is the structure is some kind of metric structure. There are ways of generalizing this, but I'm just going to stick to relativity theory, sort of ordinary garden variety relativity theory for at least the first 2/3 of this talk. So for something to survey a metric structure is just, for some matter configuration, to read off intervals of proper time as given by that metric, right? A final kind of space-time structure, which we might be interested in, but I'm not, at least for the purpose of this talk and for sort of most of the things that I in general talk about. And I think Eleanor's also not interested in this because well, she explicitly says this in one of her papers. It's something like, this stuff around us, the space through which we move, the space through which we have a kind of first personal experience of moving through. And that seems like a much larger scale project. It's extremely interesting, but it's not one that I'm qualified to engage in. It involves sort of philosophy of mind and neuroscience and various things. And I feel like there's a lot of useful stuff that you can get from just thinking about theoretical and operational spacetime, and that's sort of what I'm interested in, and that's what I'm going to talk about today. So we knock out phenomenal spacetime. We're not interested in that. We're interested in theoretical and operational. So the talk, as I present it, makes two claims, and then sort of explores some of the consequences of those claims. So the first claim is inertial structure functionalism on its own, devoid of a number of other seemingly reasonable assumptions about dynamical behavior. Things like stability of measuring devices and whatnot, and other things, other examples that we'll see as the talk progresses. So the claim is inertial structure functionalism only gives us access to theoretical spacetime. And more importantly, this is not guaranteed to give us access to operational spacetime. If we have all the inertial frames, by which I mean if we have access to local information about dynamical symmetries or information about local dynamical symmetries, that's not guaranteed to give us operational spacetime, not merely in virtue of the fact that facts about cohesiveness of matter configurations is not touched upon by symmetry structure, but for slightly more subtle reasons that we'll come to in a minute. So this leads to two questions, and that's going to form the basis of the next part of the talk. The first question is, well, if inertial frame functionalism doesn't just directly give us operational spacetime, it gives us theoretical spacetime, is that on its own going to be a useful thing? And assuming the failure of inertial structure functionalism in certain counterexample cases, does that preclude our ability to arrive at operational spacetime in those cases? So let's address the first question first. It seems to me to be reasonable to think that our interest in theoretical spacetime is down to the fact that it encodes dynamics neutral information. It's not information that's independent of the dynamics, but it's information that doesn't depend on idiosyncrasies of the dynamical field that you're considering. When you say, I'm dealing with special relativity, what that means is you've restricted your focus to a bunch of fields that are globally Poincare invariant. And so if you've restricted yourself to dynamical fields that are globally Poincare invariant, you can then make a claim about worlds for which that restriction holds. And you can make a lot of very useful and interesting metaphysical claims about those worlds. You can talk about what kind of signaling, for example, might be possible in worlds like that. You can say, these worlds preclude the existence of superluminal signaling. You can also make claims about how rods and clocks might behave under the assumption that stable rods and clocks, or sort of measuring devices more generally, exist. And that seems to be sort of a useful thing that spacetime can tell us. On the subject of important metaphysical notions, it seems like a whole lot of metaphysical notions turn on your account of spacetime and actually sort of actively use idiosyncratic features of a spacetime that you determine. So things like determinism, are our laws deterministic? Can we formulate an initial value problem? Things like causality, as I was talking about just a minute ago, can we signal in a particular way? Can this point in space-time influence that point in space? Things like that. You can know whether or not the metaphysical claims that you make about those sorts of things are true, merely in virtue of knowing what the theoretical spacetime structure is. So that seems like a useful thing, and that seems like a good reason to be interested in spacetime. So I'm going to focus on causality just as an example, because it's quite an intuitive example. And if you look at the light cone structure of Minkowski spacetime, you see that it's a direct consequence of the relativity principle, which is really stuff that's encoded in the symmetry structure, which is the stuff that's encoded in our notion of theoretical spacetime. And a further postulate, the light postulate, it's a further claim about what the invariant quantity relevant to this particular theory might be. And from that, you can now make sort of dynamics neutral claims across the board. So much for question one. I mean, we'll return to question one. Obviously, I will raise some doubts about sort of the applicability even of this concept. But more interestingly, let's think about question two, about how it is that we might think we might have access to operational spacetime. And since operational spacetime brought with it the notion of sort of being measured by stable measuring devices, I mean, that was an implicit reference to what's known as the clock hypothesis. The clock hypothesis is basically a hypothesis about the existence of clocks, which are stable matter configurations that read off proper time intervals according to some metric. And it seems reasonable to refer to that metric as the spacetime metric, although I think Patrick would disagree, and we can sort of, I look forward to the 20 minutes of discussion with you after this. So in 2013, in a paper in Foundations, Sam Fletcher proved a theorem, which he interpreted as proving the clock hypothesis for light clocks, which is to say Langevin clocks. So these are clocks, really simple clocks that consist of two perfectly reflecting mirrors with a photon bouncing between them. I say photon, he does this wholly classically, so it's sort of the classical approximation of it's sort of a Gaussian wave packet in an electromagnetic field in the geometrical optical limit. We'll come to what that means in a minute. So Sam proves this theorem in which he says, no, the clock hypothesis in all of GR is completely fine. And if it is the case that the clock hypothesis in all of GR is completely fine, then it seems like we can use light clocks to give us access to operational spacetime. It might turn out to be difficult because you might have to restrict yourself to extremely small regions of spacetime, but at least in theory it's possible. I think you see where I'm going with this. It relied on a really sort of not all that kosher assumption. Let's call it the relativistic null hypothesis. And that's a hypothesis that light always traverses null GD6 of the metric field of general relativity, GAV. Is this uncontroversially true? No. Why is this uncontroversially true? Because of the existence of a particular class of solutions to the Einstein field equations. If you want to talk about how light rays behave, if you're interested in talking about optical information to do with light, technically this is not possible using pure Maxwell theory, because pure Maxwell theory is a theory about fields. But there's an easy way to get around that. You just take an appropriate limit. So if you write down Maxwell's equations, you can derive a wave equation from Maxwell's equations. And in curved space-time, they take this form. You notice there's a curvature term in there, which is sort of important, but I'm not going to focus on very much in this talk. And so light rays correspond to the geometrical optical limit of solutions to this equation. What is the geometrical optical limit? Well, you have this equation. You consider some solution to that to the equation. It could be some, it doesn't need to be a particularly easy solution to interpret as Gaussian wave packets or whatever. But what you can do is consider sort of moving along a particular spectrum. You consider moving along a particular parameter that governs the wavelength associated with the solution. And then the limit in which that wavelength is very, very small compared to the scale over which you consider curvature variations, and the scale over which you consider variations in the amplitude of the wave, then you can prove, for a certain class of spacetimes, you can prove that in the geometrical optical limit, light rays do in fact traverse null GD6 of the metric. And so taking the geometrical optical limit of classical fields is a very, very common and intuitive and simple and powerful way of ascribing trajectories to parts of classical fields. Classical fields on their own have no trajectories. But if you're able, the sorts of things that have trajectories are things like Gaussian wave packets or sort of particular limits of wave solutions. But this procedure doesn't work in a particular class of rotating solutions to the Einstein field equations, specifically in Gödelian spacetime. There are a couple more examples, but this is the one that I'm going to concentrate on. Basically, what happens is the geometrical optical limit is not a mathematically sensible limit to take in Gödelian spacetime. Another way of thinking about this point is to say, if you've got a solution to Maxwell's equations in Gödel spacetime, and you try to do the approximations that take you to the geometrical optical limit, they knock you out of the space of solutions. So it's conceivable that the correct interpretation of this is that light rays do not traverse null GD6 in Gödel spacetime. Incidentally, the stuff that I'm talking about now is based on joint work with James Reed and Niels Linnemann. I should flag that. So as a result of this, so what are the lessons that we can learn from this Gödel spacetime example? Well, one thing is we can't simply assume that matter or light will, in the geometrical optical limit, traverse the relevant geodesic. But of course, Maxwell's equations in Gödel spacetime still have the same local symmetries as Maxwell's equations anywhere else. And in fact, they do coincide with the local symmetries of the metric field. So it's pretty clear that symmetry information on its own is not sufficient to encode the behavior of light. And this has nothing to do with cohesive forces or stability of matter or anything. But you might say, okay, well, so the geometrical optical limit isn't the right way to retrodict the geodesics of a particular metric in Gödelian spacetime. But why not try some other limit? And that's a perfectly reasonable thing to say. But I think the lesson from Gödel spacetime is you should ask that question. So this sort of gives us an interesting perspective on the role of the metric in GR. And based on this perspective, we can now return to question 1 about theoretical spacetime and see how our new considerations sort of revise what we think of as sensible answers to this question. So this is exactly what I had on the previous slide. Now, in light of what we know from Gödel spacetimes, is this still true? Well, broadly, if we have a dynamical mechanism, if we have a story of a dynamical mechanism that accounts for how matter surveys the metric, then we sort of just assume that that's there, and then all we need to worry about is theoretical spacetime, because that combined with this will give us operational spacetime. And that's what's happening in, for example, Minkowski spacetime or in Schwarzschild spacetime. Sort of well-behaved, highly symmetric spacetimes sort of give you a really, really easy connection between theoretical and operational spacetime, a connection that's so simple that you might sort of miss it. So for example, in Minkowski spacetime, you don't worry about the geometrical optical limit, because if you take any plane wave solutions of sort of any wavelength, they're not going to vary, the wavelengths are not going to vary over length scales where the curvature varies, because the curvature doesn't vary. So to whatever level of accuracy that you're interested in representing the vector fields that correspond to the trajectories of light rays, you'll always be able to do that unproblematically in Minkowski spacetime. So now, what does this say about notions of determinism and causality? Well, it sort of depends on what specific notion you're looking at. I'm not so committed to this being, to what I say, to my commentary over here being true, but I still think it's sort of broadly true for the same cases as above for broadly similar reasons, except for the notion of causality. I think the notion of causality is interesting, and this leads us to having to consider the dynamical and the geometrical approaches to relativity, to physical geometry. On the dynamical approach, this is Harvey, Brown, and Oliver Pooley's. This is the approach that sort of a lot of us in this room have been sort of arguing for or against over the last for the last little while. On the dynamical approach, it seems like notions of causality are tied to the behavior of matter fields, because on the dynamical approach, there's nothing more to spatiotemporal notions than they're encoding particular salient facts about the dynamics. So if you have a dynamical theory that tells you that, for example, light rays propagate outside of a light cone, or sort of various other weird things, that's the thing that you take seriously. So the Gödel example might, in this case, be taken to engender a violation of relativistic causality on the dynamical approach. The geometrical approach, on the other hand, which is according to which the metric field, sort of, for whatever reason, I don't want to say essentially because I think that brings in sort of unnecessarily hyper-intentional notions, but let's say necessarily, practically, for all practical purposes, plays the space-time role. On that geometrical approach, you might dig in your heels and say, no, notions of causality are still tied to characteristic features of the metric field. And so what your Gödel example shows is that the geometrical optical prescription is the wrong way to go about figuring out what the, what the metric is trying to tell us. But there are other ways that you might go about doing this. And really, what's constraining the kinds of geometries that you measure is the metric itself. And that's what I just said. But either way, the moral of the dynamical approach still stands. The moral is that the metric field in GR will not be the one that's surveyed by rods and clocks or light rays or whatever, merely in virtue of its status as a metric field. There has to be more of a story. The proponent of the geometrical approach might say, I don't know what that story is, I believe it's there. And the proponent of the dynamical approach is the kind of person who will be skeptical about that claim. And this leads us to a kind of weird reversal of the applicability of inertial frame functionalism, because it seems like it sits most naturally on the dynamical approach. But of course, here on the dynamical approach, your inertial frames are not specified by the behavior of the kinds of things that you build rods and clocks out of, because there's at least potentially a violation of the universality constraint on picking out inertial frames. Whereas if you believe that the GAB metric is itself the object that plays the role of spacetime, then you can use that to determine what your inertial frames are. Right. How much time do I have, Karen? 10 minutes. Excellent. So in the last 10 minutes, I'm going to give you a slightly more problematic case study. This is my third talk in Geneva, and I've spoken about supersymmetry every single time. Sorry, Chris. This time it's going to be much shorter, and there's going to be almost no maths in it. But there'll be some maths, and there's almost no sort of controversial physics in it, apart from the assumption that supersymmetry exists. But that's fine. And I think the first question is why think about supersymmetry? You can sort of tongue-in-cheek just go, yeah, we're philosophers, it doesn't matter if they ever find supersymmetry. But I think supersymmetry is really interesting because it allows us to embrace what Brian Pitts calls modal cosmopolitanism, a particularly useful way for philosophers to think about the world, which is, let's stop imagining that all of the possible space-time theories that might be interesting are in sort of significant respects like the ones that we already have. Let's sort of move outside our bubble a bit. I think superspace and supersymmetry is just a good sort of testing ground for some of the sorts of claims that we make about space-time. And in particular, in this case, I want to see what supersymmetry and superspace have to say about theoretical space-time. Really quickly, supersymmetry is a quantum field theoretic symmetry between bosons and fermions. Insofar as it's a symmetry, it preserves the form of the dynamical laws. But you can think about this in one of two ways. You can think about this dynamically, by which I mean you can think about the supersymmetric transformations as just transformations from bosons to fermions that leave the form of the equations of motion invariant, alternatively, that leave the form of a Lagrangian quasi-invariant. And as a consequence, they map solutions to solutions. Or you can think about it as a space-time symmetry in the sort of standard kind of John Ehrman sense. It's a set of, the Anderson-Friedman-Ehrman sense. It's a set of transformations which leaves invariant certain objects characteristic of space-time structure. So, for example, the Poincaré symmetry of Minkowski spacetime is something that leaves the Minkowski metric structure invariant, and in virtue of that is a spacetime symmetry. So in ordinary spacetime, you coordinatize an event using a quadruple of real numbers. In sort of high-dimensional spacetime, it'll be an n-tuple. And then a classical field, or, well, any field, is a map from this space of events, space of independent variables, to some mathematical space. Quantum field theoretically, a bosonic field is a map to a space of commuting operators, a fermionic field is a map to a space of anti-commuting operators. But if we're only interested in this sort of commuty, anti-commuty type behavior, then we can consider classical analogs. We can just take sort of the classical limit. And by that I just mean, let's imagine a world in which we had classical fields that took values in spaces that are either commuting or anti-commuting. So you just imagine that there are numbers that commute and numbers that anti-commute. This can be made completely precise, but I don't think there's any point in sort of really going into the mechanics of how that's true. So one way of understanding why a standard space-time manifold coordinates commute is by thinking about how in classical field theories, all of our classical fields commute. And so the commuting behavior of our field is reflected in the commuting behavior of our manifold coordinates. And so for classical non-commuting fields, if this behavior is universal, then it seems like a perfectly reasonable thing to do to bring the non-commuting behavior or the anti-commuting behavior onto the space of independent variables. And in a sense, this is exactly what we do when we consider Minkowski spacetime. We're taking dynamical symmetries of matter fields and we're reflecting them in our manifold structure. Superspace is this, arguably the best spacetime setting for a supersymmetric field theory. And it's an extension to ordinary Minkowski space. It's just got the four ordinary Minkowski coordinates, and it's got four anti-commuting coordinates. So over here, we found ourselves in a scenario where the same sorts of moves that we make in GR, where we link sort of dynamical and spacetime symmetries, perhaps as a consequence of being inertial frame functionalists or whatever, is a sort of move that's available to us in spacetime as well. In superspace as well. And so now we could ask the question, do notions of causality, because that was the thing that I concentrated on earlier, do notions of causality, are notions of causality tracked by our identification of theoretical spacetime structure? And perhaps surprisingly, we find that the answer is no. For the reason that the extra dimensions of superspace are not straightforwardly spatial in the way that the non-temporal dimensions of spacetime are spatial. And this is the only bit of maths, but I think it's fairly clear what's going on. If you've got, recall that the thetas were the anti-commuting coordinates. If you want to sort of impose what's known as a super translation, so a translation both of the anti-commuting coordinates as well as the commuting coordinates, you find that no amount of moving around through the ordinary commuting coordinates, through the x's, is going to affect, brilliant. So no amount of moving around through the x's, no amount of generating translations using the momentum generator is going to move you around the anti-commuting coordinates. But a super translation, which does move you through anti-commuting coordinates, also non-trivially moves you through the ordinary spatiotemporal coordinates. What this means is that the presence of these anti-commuting terms means that space and time are no longer orthogonal, quote-unquote orthogonal, in the way that they are in Minkowski spacetime. And now if we think back to Minkowski spacetime, if we think back to what the orthogonality condition of space and time was doing in Minkowski spacetime, it was allowing us to articulate a light postulate. So we still have a relativity principle because we still have a symmetry group in superspace. But the associated relativity principle on its own, in the absence of a like postulate or an equivalent, can't ground the distinction between time and space in the same way as you could in Minkowski spacetime. And that's because, insofar as we imagine light in superspace will be governed by some kind of supersymmetric extension to Maxwell dynamics, we can show that super Maxwell dynamics does not have the equivalent of a light postulate. The light postulate, incidentally, just the claim that the two-way speed of light in a vacuum is invariant. I should have mentioned that when I mentioned it earlier. Anyway. And so now we find ourselves in a position where we've done all the things that the inertial frame functionalist would do to get theoretical spacetime. And we've arrived at something that's a theoretical spacetime. But we found that it's not quite as useful as arriving at theoretical spacetime in special relativity. And that's because the attendant dynamical features that we could sort of take for granted when doing our metaphysical theorizing in special relativities are no longer present. And so that's why it's interesting to look at superspace. And so to conclude, on time, I believe, we need to be careful about the work that we think we can unproblematically assume that our spacetime functionalism can do. So theoretical spacetimes can, but they do not always ground concepts like causality and determinism and whatever. They do in certain well-behaved theories, and there's a large class of well-behaved theories, and that's why spacetime functionalism is really, really good and useful and important. But it's also important to realize where this falls apart, and in virtue of what this falls apart. And be cognizant of the domains in which we actually do just need to do the physics. We do need the full dynamical story. I'd like to just conclude with the idea that the failure of spacetime functionalism is not a failure of the utility of the spacetime concept itself. It's still unproblematically picking out at least the theoretical spacetime concept. I see it more as a failure to pick out, a failure of the spacetime concept itself to be useful in a certain type of metaphysical theorizing. And I think that's all I wanted to say. So thank you.
Thanks, Tushar. Questions? James?
Are you saying that inertial structure spacetime functionalism gives us access only to theoretical spacetime in the gut case? That would seem too strong.
It kind of depends on whether you go dynamical or geometrical.
So I mean, what the example shows is that one can't construct a Fletcher-style light clock, but that doesn't preclude the other kinds of light clocks or clocks which approximately satisfy the hypothesis, or clocks which only work in inertial frames, blah blah blah.
Yeah.
And it seems like all of that, if those kind of things exist, would suffice for inertial frame functionalism to give us access to operational spacetime in the curve.
I completely agree. But I mean, the point of this was just to say you need that story, and what we've taken to be the thing that fills in that gap has been things like the geometrical optical limit. And really, this is just a counterexample to, so first of all, the idea is, things like light clocks are often taken to be sort of ideal clocks, at least theoretically speaking, and sort of really simple, and so therefore allow us to theorize kind of unproblematically. So we've got this unproblematic notion of a light clock, we've got this unproblematic notion of the geometrical optical limit. And that might seem to be the kind of thing that will ground your inertial frame functionalism, and all I'm trying to say is, in that particular case, that's not what's happening. It may happen in some other case, but if you're convinced that it's going to happen in some other case, then I think you're convinced you're committed to a geometrical, to embracing the geometrical approach. If you're more agnostic about that, then I think that's characteristic of the dynamical approach.
Okay.
Yeah, I'd also like to kind of inject some things we were discussing over lunch, because I think one more I want to take from what you were saying is we should distinguish very clearly between this operationalist approach to functionalism and theoretical functionalism. And in a sense, one could say that common sense functionalism is exactly the functionalism that turns on the operational role, with the folk theoretic platitudes being the operational definitions, whereas theoretical functionalism, as you call it, that's more about well, analysing the conceptual roles that certain theoretical terms are playing. So I think it might be very interesting to discuss this distinction between, or this link between common sense functionalism, understood as drawing on the operational role certain concepts play, and theoretical functionalism that is focusing on the theoretical role. It also touches a bit on the question we were discussing in the last talk with James, that spacetimes in which there are no rods and clocks, okay, then operational functionalism doesn't apply there. Yeah. But we could very well make the case, for the same reason why you were rejecting common sense functionalism, and most people in the room probably would reject operations per se, well, that means we should go for the theoretical functionalism instead.
Yeah, so I mean, in a lot of cases, theoretical spacetime will give you sort of, at least practically speaking, might be a necessary step towards constructing operational spacetime. That's true. And if you have no rods and clocks, it seems like basically the motivation behind sort of thinking about things in these terms is to rule out what I think, what I consider to be sort of an unnecessary restriction on the spacetime concept, which is to say, if you don't have rods and clocks, if you don't have stable bodies, then you don't have spacetime.
Yeah.
So I want to just push back on that a little bit. I think that operational spacetime is very different from something like a common sense set of platitudes. I mean, ultimately, if you think that what we're doing when we empirically theorize is that sort of physical salience or representation relations all stem ultimately from empirical results, it's a really integral part of the theoretical project to work out how it operationalizes a theory. And that's done in a way that's a very long way away from the layman's common sense. It's done in a highly specialized way. So I think it's really important that that's very different. The common sense platitudes have more to do with something like the phenomenal role that you were picking out. And I think it's rather important to divorce those two notions. I think I can see that it's useful in some situations. I mean, I think it's the theoretical spacetime versus operational spacetime distinction, I think, can be very useful in certain situations where we're a long way away from operational significance. Mm-hmm. And you want to point out that what's happening is you have some piece of structure that's playing the same role that the thing with operational significance does in this other role, and it's space-time in that sense. I think that's helpful, but I think that trying to think about the project as one of operational significance being sort of segregatable from the theory is just not the way to think about how any of our theoretical terms get meaning or salience in the first place. So I think I think there are purposes for which you can divorce these two things, but you want to be very careful of thinking of these as sort of disconnected projects, lest you make a nonsense of how theories get any purchase on the world at all. But you don't have to be an operationalist to think that the physicality or the salience of theoretical terms in highly theoretical constructs comes ultimately from their relationship to the operations. Yeah, I completely agree. But that's sort of perhaps it didn't come across in the way that I presented it here. But one of the reasons that I'm interested in the theoretical spacetime is because there's a lot of physically salient information in the symmetry structure of a dynamical theory. There's a ton of it, and I don't want to just sort of throw all of that away and say, yeah, but until you give me a pointer reading, I'm not going to consider that information to be sort of physically useful or physically salient. I think that's sort of why I think that's sort of what motivates this distinction between theoretical and operational. Not so much I don't so much want to think about theoretical spacetime as sort of a massively impoverished sort of halfway house towards operational spacetime. I still want to think of that as being something that is a result of being interested in sort of important physical characteristics across sort of that are shared by a variety of fields in whatever theory you're considering.
It's a question. Is there? I cannot see why the optical geometrical approximation failed in ordered spacetime, because it's totally related with the global behavior of the spacetime.
So I
cannot see how this can fail.
So there's a recent paper in classical and quantum gravity by by two physicists, Arsenio and Hodgman. I think should have the reference here. Yeah, it's the first one up there. And yeah, basically they show in that paper that so basically what's happening over there, sort of really briefly, is when you take the geometrical optical limit, or when you make the geometrical optical approximation, you're basically doing a two-scale approximation, right? You're saying you're considering wavelengths that are smaller than the things that I said earlier. And from that, you derive the dispersion relation that says kmu equals 0. In Gödel spacetimes, and they're not clear about exactly what the reason for this is. They conjecture that it might have something to do with rotation, because a similar result goes through in Kerr spacetimes. But in those spacetimes, the approximation, the geometrical optical approximation, is inconsistent with the dispersion relation being kmu equals 0. So that's the sense in which electromagnetic light doesn't travel.
To look for it, because locally it's difficult to understand, because if you have locally model space-time is equal to any other space-time, and then if you just imagine that this optical geometry, you just think about some emitter that is sending a signal to another receiver, which is close by. Then if you analyze only this trajectory, I don't see why it should be a problem here. Another thing is that if you analyze the entire space-time, because if you analyze the global properties of that, then for sure this space-time is very...
Yeah, I mean, it's got insane other features. Yeah, I agree. Yeah, I mean, the answer to exactly where it comes from me is I don't know, but I'm perfectly perfectly convinced that it's willing to be convinced that it's sort of global features of.
It's only because it is very important. Because if you are not able to really analyze trajectories locally, to the very notion of geodesics is in trouble.
Yeah.
Also, maybe a completely stupid question. I mean, is electromagnetism well defined on Gödel spacetimes? I mean, especially the initial value problem.
Another thing is that I think it's very difficult to analyze.
Yeah.
You have close to left.
Yeah, but if the initial value problem is not well defined, so what? I mean, then the whole question doesn't make a lot of sense.
I mean, in general terms, I will not take this example of stuff, because this is model spacetime is a counterexample of yeah.
Other questions?
Maybe it's worth mentioning that they sort of the Kerr spacetimes in that paper.
Yeah,
Did you say that?
I did, yeah.
Oh,
But I sort of slipped it in.
Then again, a similar question arises there, because it seems like locally in a Kerr spacetime there shouldn't be a problem with the geometrical optical limit. So what is it exactly that?
That's why I would like to know the details of that. Because Kerr spacetime also they have close curves in some region versus spacetime. Maybe the problem is a global that you cannot define global solutions of this limit.
Yeah.
But this is a different thing. If this is the case, I would not say that this is meaning that there is a failure of the geometrical approximation.
Yeah, in Kerr-Newman spacetimes, of course, if you have a maximal analytic continuation into that areas, then of course, then it becomes like other spacetimes like that, and a counterexample to many things as well. But it seems if you just look at least the asymptotic region or that outside of the event horizon, there shouldn't be a problem, I think. And then it becomes a funny question. I mean, Gödel spacetime is special in the sense that the region of chronology or causality violating possibilities of CTCs is global. It's the whole spacetime, but that's not the case for the Kerr-Newman spacetimes. So how could it then be that somehow the presence of that strangely behaving region can somehow nevertheless screw up the geometrical optical limit outside in the apparently well-behaved, causally well-behaved area?
Yeah. On the base of the co-annuity, this theorem is supposed to break down only certain regions.
I don't know, I haven't read the paper, but
I think you have to make a certain wave ansatz for which they show that the velocity or the
a certain
certain wave ansatz for which they show that the geometrical optical limit fails. But this doesn't mean that necessarily all kind of waves exist in space-time don't have a well-defined.
Yeah, it's an ansatz about a specific solution because it's basically intended to be a counterexample, and so it's a particularly simple, well-behaved sort of plane. It's basically a plane wave ansatz that they make, and then they show that if you were to take the geometrical optical limit of that, then the condition that the two length scale approximation holds, and the condition that the dispersion relation is k mu equals 0 are inconsistent.
So this intuition, if I may,
Sure, yeah.
is an interesting input because it puts into question whether this ansatz is really all what one should be interested in.
Yeah, that's it. I agree.
Any more comments?
I agree too much.
All right.
yeah, really, that's
I guess we'll thank Tushar again and then have a